So here I have recreated the diagram from the previous video, and I have drawn in here the pathways that we have identified as those that do not carry a minus sign, and we said to each of these four pathways we also have corresponding complex conjugated pathway. This means, if I translate that into an equation, that our third order response function depends on three, or is a sum of four contributions. Each of these contributions, they have a form of the response function. They are just part of it, just result of certain ways how we divided the actions of the commutators from left and from right. So we would have contribution of four terms. Each of the four terms actually look as a sum of a term and its complex conjugated term, and there is a minus in front of all the complex conjugated terms. So these things here, these four different things, are called Liouville pathways, or actually one can draw it this way too, Liouville pathways. And out of them, they sort of form response functions themselves, or parts of the response functions. Our response function is composed altogether of eight Liouville pathways, and we have four types of Liouville pathways that are independent. And we need to kind of have a look at each of these pathways separately. There is, of course, a nomenclature used here, certain type of nomenclature that makes sure that everybody, when we talk about the pathways, we use the same things. So we have indeed we have R1, R2, R3, R4, and they are very specific pathways in that diagram up there. Let's notice some things. So basically that's the way which helps me to remember what these pathways are. So they all start here, GG. Well, there's basically no way out of it. And then then the pathways, some of them after two actions go through either the ground state or the excited state. This one goes through the ground state, so this is ground state, and these two go through the excited state. So that's one way how we can split them into groups. And then another very important characteristic is whether this first coherence intervals, you see that here the E and G is not the same state. So here we are, if it were if it had represented an element of the density matrix, this would be a population of the ground state, this would be population of the excited state, but this is a coherence element. These states here are different, and you can see that sometimes you have EG and EG2 at the end of the pathway. On the other hand, here we have GE and EG. So whenever these things here, the elements or the brackets here are the same, we call these pathways non-rephasing. When they are different, like here, we call them rephasing. And there are two non-rephasing and two rephasing pathways. We are now talking only about the R1 to 4, those which are not complex conjugated. This is something that also has a very big importance later in spectroscopy. Now it's not important to know what is what, but it will come important later. Now in order to, this is a very complicated diagram. We have another quite a complicated diagram that we can use to denote these pathways, and on them I will try to really show their names. So we have a diagram in which we let the time run up. So this is time running up, and these arrows here, along these arrows we write the density matrix elements that are involved in there, or the bra and cat of the state in which, or the, you know, this fraction of the state a part of the perturbation series that we are looking at. So we all start with GG, and we start with left or right interaction of the incoming field. So if we go up here, for example, this pathway starts with the action from left, and all the actions are happening from the left, and during that this right hand side, this bra doesn't change at all. So we can draw it this way. We can actually say, well, then here we have the diagram, here is the photon coming, or the interaction with the field coming, and this thing excites us into EG. It excites the cat part of the diagram into E. Then the next step, as we could see up there, would be something like the excitation. So we have to get rid of one photon, and we arrive at the GG. The next step is again an excitation, E, G, and the last step would be something that I'll denote by something else, because that's not an interaction with the field. Here we calculate the polarization. So this gets us back to GG. So this is a diagram of of a non-rephasing pathway. Non-rephasing pathway, because EG, they are different, they are the same, and this pathway we denote by R4. This is for historical reasons. Don't ask me why this is 4. Well, it came to us as the first that we look at, but in fact it's for somebody else the last one. So this is the R4, and it's non-rephasing. It goes through the ground state also. Let's look at the other cases. So let us take, let's say, this one that has two interactions on the right and then one on the left. Two interactions on the right and one on the left. That will be very easy to achieve. Again, so first interaction on the right will bring us to E. Then we have to have another G, and then there is one on the left, and well, we go out. That already doesn't count. So here we have E, G, and this brings us back to G. This pathway goes again through the ground state. It is, however, rephasing pathway. We will see sometime later around photon echo why this is called non-rephasing, rephasing, and this one non-rephasing, and so on. And this is a pathway that is normally denoted as R, as R3. It's a rephasing pathway, also goes through the ground state like the R4, but it's a rephasing one. Okay, let's go to another. Let's go to pick another one. So let's say this one, which goes once from the left. No, that's the one that we just did. No, once from the left, then twice from the right. Once from the left and twice from the right. Once from the left. Once from the left. And twice from the right, and then out. So GG, here we have EG, E. Now we lose this one, so we already see this is gonna be in the non-rephasing. That's why I draw it here. It's a non-rephasing pathway. We again end up in G. non-rephasing pathway, as we see, goes through EE, and this one is called, or is usually denoted as R1. Well, and the only thing that is left in here would be a pathway that is rephasing and going through the excited state. As we have seen, or we can already guess, this rephasing pathway will start here on the right. We'll have to end up in the excited state too. So now we will have to, because this has to be positive pathway, so we have to have two interactions from the right. There will be G E. Also we want it to be non-rephasing, rephasing, that's here, and things go out, and this is a pathway called R1 and is also rephasing. So again, just let me summarize. These two go through the excited state, these two go through the ground state, these two are rephasing, so these things are the same here, whereas these things are non-rephasing. You can see that the excitation is on the other side of the bracket. These differences will be extremely important in discussion of the third order nonlinear signal. It will tell us from like where the signal goes even directionally and so on, where the, well, not really directionally, but it will tell us, for example, whether the signal that we are observing corresponds to things like stimulated emission, excited state absorption, ground state bleach, etc., etc. But for the details, let's wait for the next video.